everybody for coming. Oh, okay, I'll thank everybody now. I want to thank everybody for coming. So this is EDF's economics seminar. Protecting local water quality has global benefits with John Downing and Steve Newbold. I want to thank them for coming. Like I was just saying to them, I saw this paper. It's co-authored with somebody that I know, Sheila Olmsted, and I read through it, and I thought that this was something that was definitely something that needed to be talked about at EDF, and I feel like we're just very lucky to have them here. It's a paper that I think is really worth talking about. Steve Newbold is Associate Professor of Economics at the University of Wyoming, and John Downing is at the University of Minnesota. He's Director of the Minnesota Sea Grant Program and a Professor of Biology at the Large Lakes Observatory. Steve and John, I will yield the mic to you, and then throughout the presentation, I'll advise the attendees, if you have questions, can you please direct them to chat? I will be monitoring chat, and then periodically, strategically interrupting them with the questions during the talk. And then at the end, we'll have about 20 minutes or however long we need to ask questions of these two academics. So again, Steve, John, thank you so much for being here. Really fortunate to have you. So take it away, please.
I'll just get things organized here, and I'll kick it off and then turn it over to Steve. I was partway through my slides, and so I have to just sort of reorient back there. Thanks so very much. I really appreciate the introduction, and this has been really fun to work on, as it's a collaboration, but really across fields. Are you seeing a presentation view or presenter view at this time?
I see a presentation view right now.
So you're seeing just one big slide, is that correct?
One big slide, yeah. Looks
marvelous.
Great.
Well, that's what it's supposed to do, and that's why Hillary and I sort of queued it up. Well, the way we're going to do this is, first, just a quick introduction of who we are, and then I'll go through some slides, and then I'll turn it over to Steve. I'm a limnologist or biogeochemist, depending on sort of where you come at this from. And Steve's an economist. I figure you all know what an economist is, so I thought I should probably tell you what a limnologist is. Limnology is a study of lakes, rivers, and wetlands as systems, and comes from a book that a colleague and I put together. Biogeochemistry is dealing with the relationship between the Earth's chemistry and its flora and fauna, including circulation of elements throughout the biosphere, throughout the environment. Not that many people know what limnology is, but if it's sort of like oceanography for inland waters. And so that's the field that I've studied for 30 plus years. So we love lakes like this. I hope you all do. This is a beautiful little lake, one of my favorites. But knowledge of each one of them, which is what limnologists generally have done just by themselves, is pretty much meaningless to global environmental problems. None of them are, other than maybe our friend Lake Superior out here, which is 11% of Earth's surface freshwater. Other than big lakes like that, each lake is probably not very relevant to a global environmental problem. And the reason that I'm really interested in lakes in a sort of a global sense is that I see Earth sort of like a chocolate chip cookie. Limnology has shown that inland waters are active particles embedded in the inactive matrix. If you're like me, you like the chocolate bits more. They're sort of active in a lot of ways in terms of sugar and other kinds of nice things. But the thing is with lakes is that rates in lakes are typically 100 to 10,000 times faster or more efficient than they are on land. So they're active particles in a relatively inactive matrix. Steve and I are going to talk about four things today, and I'm going to kick it off with sort of the natural science part. And then I think then Steve will go on with the sort of social cost issues. But I'm going to talk about how lakes are drivers of greenhouse gas emission and therefore climate change. And then we'll take that stuff and ramp it up to global and talk about how much eutrophication is going to change So eutrophication, for those of you who are unaware, is the effect of excess nutrients basically on the productivity and sort of greenness of waters. And then Steve will take it away with talking about how much a social cost there is from eutrophication-driven climate change. And then we'll talk a little bit about how the value of avoiding that compares to other social values of lakes. And as I said, this has been really fun work to do. I've had the natural scientists don't always get the chance to work with economists, and I've been very, very delighted to do so, and I hope it's reciprocal. So lakes they help regulate global carbon and greenhouse gas flux in a variety of different ways. One is that they're really active in emission rates of CO2, CH4, well, carbon dioxide, methane, and nitrous oxide. And they'll take it up and they'll give it off depending on what's going on in the lake. They're also really important in carbon sequestration and sequestration of other elements down in the deep sediments. And then they convert carbon and other elements within the lake and send some of it downstream. So they're, as I said, they're active particles, but they're active in aspects that are relevant to the global carbon cycle and to climate change in general. I'm a global limnologist, so I should tell you what global limnology does. And it basically quantifies and understands the role of continental waters in the functioning of the overall biosphere. It includes a variety of aspects, how these are influenced, how these rates are influenced by human activities, and developing tools to do this kind of thing. It's a relatively new field. I sort of defined it in about 2009, something like that. And so a lot of us out here are trying to do those sorts of global limnological things. So global limnology addresses this. It's the difficult part. It's like, and then a miracle happens. You make measurements locally, and then you need to scale them up some way to the biosphere. And the devil is definitely in the details, as I will show you in a minute. But that's what global limnology tries to do. So the simplest and now traditional upscaling approach is to make an assumption that each place in a set of global ecosystems has the same value of Y, whatever that is that you might be interested in, and we believe that Y is an unbiased estimator of Y bar sort of for the planet. N is a number of systems, the total area or total volume, depending on the units of Y. And so you predict the global rate as a product of Y bar times the number of systems. And I think, and as I say, I'm not an economist, but sort of this would be like the economic equivalent of this would be to say that we're calculating the global GDP from the average GDP of 10 countries and multiply it times the number of countries in the world, which I think you all would appreciate is a somewhat dicey estimator of gross domestic product. So upscaling varies a lot in complexity, and that's what we do. In reality, rates like greenhouse gas emissions vary with all kinds of characteristics of ecosystems. And in my case, we're pretty interested in lake size. And obviously, since we're talking about nutrient eutrophication, we're interested in nutrient concentrations, but other variables have an effect too. So the predictive relationship concerning Y is something like Y hat as a function of a bunch of stuff. And I think Steve is going to do most of the math, but this is as advanced as the math gets for us. Therefore, we can calculate an upscaled or global rate from the probability density distributions of those variables that drive that rate that we're interested in. And in the case of Steve and I, we're really interested in methane emission, well, also CO2 emission and nitrous oxide in some cases. There are lots of reasons that we need more and better global inference. One is water will take more human abuse in the future and will be altered by global changes. And that abuse, for example, we'll talk about today, nutrient pollution will change the global role of inland waters on many rates and processes. And I'm going to try to give you some estimates of how much those will change between now and 2050 and 2100. This all started, this kind of upscaling work started with work with Tanya Del Santro and Jake Boulier And we wanted to estimate global greenhouse gas emissions for lakes, and made the best estimates there have been to date. We could do this because sensors were improving, a lot more estimates were being created, and previous global estimates were calculated as basically those average rates times global lake area, which assumes that these average rates, mostly measured in Nordic countries with pretty clean water, are that these rates are representative of all lakes. We know that aerial emission from lakes is not constant, but has a lot of covariables. So how did we do it? We collected 8,000 or so worldwide estimates, including carbon dioxide, methane, and nitrous oxide emissions from the published literature. And then we just did some simple linear and multiple regression against lake size and eutrophication rate, or trophic status, as it's called in some of my next slides. And this can be measured by chlorophyll concentrations in the water, the greenness, by phosphorus and nitrogen, which are the principal nutrient drivers of eutrophication in inland waters. And then we calculated a globally weighted total emission by weighting with lake size and productivity, probability density distributions. And the productivity itself was inferred in this case from satellite-derived chlorophyll estimates or greenness of lakes, and lake size distributions from a bunch of things, including one of my papers and two other important papers on world lake size. So I'm going to show you about three slides that are going to show you how the three different greenhouse gases vary with lake size and trophic status or eutrophication. And they'll all look about the same, but they'll have kind of different scales. So just a minute, I'll do that as soon as I get done coughing due to the lovely virus that my grandsons brought me. Hang on just a second. I don't even know how to mute on here right now. So anyway, you're going to have to listen because I can no longer talk. It is not COVID, thank goodness, but they brought me something else fun. So if you consider carbon dioxide, which is what Congress and a lot of other people consider to be the major and important greenhouse gas, those CO2 fluxes decrease with lake size, and the effective trophic status differs between large and small lakes. The red on this three-dimensional plot shows high rates of CO2 emission. This axis here is trophic status, more eutrophic up to the right here. And this is surface area, big lakes here. So we basically have a response function that can tell us how, in general, across the Earth, how CO2 emission rates vary with those two important driver variables. Methane is really different. There is really no lake size effect for methane. Big lakes and small lakes seem to emit methane at about the same rate, but trophic status has a very pronounced effect. What does that mean? It means that clean waters down here, very clear waters down in this area, are not emitting much methane, but as we make them more eutrophic, add more nutrients to them, make them greener, then the methane emission rates climb really fast. And these are log scales. So just to give you some sense of how quickly these things go up. So emission increases with trophic status, and there's no lake size effect with methane. And this will be important in a second because I'm going to show you how important methane is in global lake emissions. Nitrous oxide emission increases with lake size and trophic status. So the highest nitrous oxide emissions are in those very nutrient-rich lakes that are very large. And that's because they're building reactors for the emission of laughing gas or nitrous oxide. So the functions are really different. But we could create then, if we use this global chlorophyll map, and Steve and I are going to show you a local chlorophyll map in a little bit here, but we created a joint lake size chlorophyll phosphorus probability density distribution. And then we just multiplied it times those fitted functions that I showed you in the previous slide. So it's pretty simple stuff. And what we found was that the more complex lake size productivity weighted estimates are better predictors of emissions. And these numbers are in teragrams per year of carbon or nitrogen. And teragram it's hard to imagine, but it's really a lot of stuff. And what we found was these ranges of upscaled gas emissions, and our methane emission included both diffusional losses of methane from the water, and ebullition or bubbling. So, and the differences, the ranges here are given simply from the different lake size distributions that we assumed. But our estimations showed one important thing, is that people have been overestimating really the importance of CO2 emissions from lakes on the atmosphere, overestimating the influence of nitrous oxide emission on the atmosphere, but underestimating by about half the impact of methane emissions. So methane is a really important variable and is emitted in important quantities. Now, methane, the reason that's important is methane is atmospherically really active compared to CO2. Depending on time scale, it can be orders of magnitude basically more important on the more impactful on atmospheric change. So the atmospheric impact is high and dominated by the impact of methane emissions. And that's sort of the bottom line that we found out here. About 3/4 of the atmospheric impact is driven by methane, about 1/4 carbon dioxide, and a little bit by nitrous oxide. So methane is the variable to watch with respect to lakes, and methane is the important variable to watch with respect to degradation of water quality. So carbon emission in the atmosphere is only about 10 to 15% methane, but methane's effect is large compared to carbon dioxide. And the effect will increase with global eutrophication, which got our attention, got us concerned about how much eutrophication might change into the future. Just a sec. So how do we go about figuring that out? Steve and I can calculate what the impact of current eutrophication is on the social cost of methane emission, but how about in the future? So just as a brief overview, with respect to water impact, people do only 4 important things. They eat, they excrete, they make more people who eat and excrete, and they alter landscapes and climate. So that's, you're looking at this third image. I have no idea why anyone would get that many babies together, but in any case, I needed a demonstration of the reproductive part. And so it's important to note that every time we put another person on the planet, we're creating a new excretor, essentially, that will change the value of the quality of water. So first, before I talk about Olympic swimming pools, I want to talk about hockey. They're kind of similar sorts of things, but I like to say you don't really appreciate a hockey stick until you've been hit with one. I spent 20 years of my career in Montreal, which is why I'm showing the Habs here. But you can see a lovely hockey stick there. Now, here's another hockey stick. And this is the hockey stick diagram that shows the departures in temperature from global averages. So you can see the very hockey stick-like increase in temperature. But as my friend Steve Carpenter, who's a limnologist at the University of Wisconsin, loves to say, it's basically raining hockey sticks. It's not just temperature. It's also urban population, rural population, real GDP, global water usage. A whole bunch of things are changing in a hockey stick-like accelerating fashion. So this is why, because of population growth, this is why we are expecting a very large change in water quality in the future. So each person, I said a minute ago, each person excretes a lot of nutrients. And this is getting kind of personal, sorry, but each person excretes enough nutrient each month to make an Olympic pool of distilled water eutrophic. I'll let that sink in for a second. It's a remarkable thing. It doesn't take much. It takes 30 parts per billion to turn distilled water into a eutrophic system, essentially. So every month we go from that to this with the excretion of phosphorus by one person. Each person puts out something like a kilo of phosphorus a year. And the details are in there about how we calculate this, and it's all pretty gross. But the point is, every time we put a new person on the planet, we're releasing a lot more nutrient. It's a two-edged sword. People need food. Food releases nutrients to the water. We give food to people, and they release nutrients to the water. So that's how eutrophication happens via population increase. Tanya Del Santro and Jake Bollier and I wanted to project how much it will change, and I'll try and make this quickly so we can get to the juicy economics quickly. But we there are two kinds of things. Eutrophication and methane emissions increase in two sorts of ways. One, we're increasing nutrient loss into water from increased human activity. That's one. The other one is we increase the relative effectiveness of nutrients through altered global environments. So for a unit phosphorus, we're going to get more impact. We noticed this in northern Minnesota a lot this summer. It's been very, very warm, for example, and we're expecting it to get warmer and warmer. Same amount of nutrients yielded so much more algae that we're now getting algae blooms in Lake Superior, and some of them are showing toxic materials, and that's one of the most oligotrophic or nutrient poor systems on the planet. So there's an effectiveness issue driven by climate change, and there's also that human excretion issue. As we increase population, we're just releasing more via agriculture and human effluent. So how much and what's driving it? And I won't tarry too long on these. Just I'm showing about how much the nutrient levels are supposed to increase by 2050 and 2100 from some futuristic work. Population growth will be driving river nitrogen export, pumping up nitrogen by 2050 to by about 23%, and 41% by 2100. Phosphorus runoff due to food production demands. Tillman et al. In a Science or Nature paper suggested it's likely to go up by 270%, essentially to 270% by 2050. Manure and urine export from animal agriculture will increase substantially, as will just simply population growth and population impact, depending on a few non-utopian assumptions and food production and sewage. So nutrients will increase. Now, there are multipliers of the effects of nutrients, and they are due to things like increased nutrient mobilization from climate change due to storminess will pump up the amount that's lost. Increased nutrient delivery due to temperature and storms, also from another paper. Another estimator about the same of a multiplier of projections. Storms will increase nutrient delivery. They will also, just simply because of increased temperature, productivity is likely to increase per unit nutrient by about 30% by 2100. And also, we don't think about it too often, but we're likely to increase the amount of water that we'll have on the surface of the continents by something like 5% by 2050 and 10% by 2100, due to things like increased runoff, lost permafrost and ice cover, and things of that nature. So if you take the aggregate of these, and this is a little bit hard, let me just go to the next slide. If you look at the future lakes atmospheric impact compared, let's go back. Basically, by 2050, we should see an increase of an aggregate effect of nutrient release and increased temperature, increased storms, etc., by something like 30 or 40% to well over 200% by 2050, with if you consider both the nutrients and the multipliers, and of course much greater by 2100. So these are the kinds of projections Steve's going to share with you with the social cost, although we took some pretty conservative approaches in the social cost estimates not the extremes, clearly. So the future lake's atmospheric impact compared to other important sources and sinks suggests that methane impact will be something like a third, up to about a third of fossil fuel burning, and around 150% to 260% of land use change by 2050. This will counterbalance up to 100% of oceanic carbon burial and up to 100% of all terrestrial burial, just to give you a sense of these being pretty important numbers. So this is Steve's bit now, and I was really lucky to be at a meeting with Steve Newbold, Steve Pulaski, and Sheila Olmsted. And I talked to them about methane, and they talked to me about social cost, and we have been having a lot of fun with that ever since. Steve, if you want to just let me know when to change slides, I'll be glad to do it. And so I turn it over to you, Steve.
Sure. Okay. Thanks, John. I am unmuted, so I think you can hear me. Okay, you wave if you can't, I'm sure. Yes, this was a fun project, and this is, you can linger on that first one for a second if you want.
It changed changes itself. I don't know.
We might have to put a leash on it if necessary, but I was just thinking, as John was talking, I was reminded that oftentimes when economists are asked to work on these interdisciplinary projects, it takes the form of a lot of science is done, and then at the end someone has the idea that maybe we should put some economics in here somehow, and so they find the closest economists and say, can you do a benefit cost analysis on this, or can you put a dollar value on these results we have? And in this case, that's actually not super far from the truth, but it happens to be a case where that approach works pretty well. So because we have, what I'm going to talk about is the social cost of methane numbers that were married in a very simple way with all the projections John just talked about. And, by design, that's how they're intended to be used. Social cost numbers are these really rolled up estimates of economic damages from an extra ton of emissions of a certain type of greenhouse gas. And so John has produced all these projections, and other folks, a bunch of economists, have produced estimates of these social costs that can be multiplied. So that's what we're going to do. And there's not a whole lot to say about that process, but there's a little bit of background that I'll give you on, integrated assessment models and social cost estimates, just to sort of flesh out that background a little more than is needed in the paper itself. So yes, these are other economists on the team. They weren't able to join us today, but they did a lot of the work on the economics part of this paper. So let's see, I think everything else that's said here may come up again if needed. So let's go to the next slide, John. Okay, yeah, so our part is to sort of go from the biogeochemistry that John just talked about to economic value. And like I said, we use estimates of the social cost of methane, also CO2 and N2O, but methane is our sort of headline greenhouse gas here. And we're using, when I say official estimates, I mean US government published estimates that came out of the interagency working group on the social cost of greenhouse gas process that started in 2010 or so. I was in a previous life, I worked at EPA, and so I was following that closely and working on some elements of that process. I just can't remember the dates. But that interagency working group ran several integrated assessment models, which I'll talk about in a minute, and tried to use I shouldn't say consensus values because there's not consensus on all elements of those, but sort of middle of the road values. And when sensitivity analysis was done, in particular on the discount rate, which is a huge economic, very important economic parameter in those models, they used 3 values that were trying to span the range of what at least most folks think are plausible, and produced a sort of library of social cost estimates for not just CO2, but also these additional greenhouse gases, methane and N2O. And so the way to think about these social cost estimates is, as the second bullet tries to describe it, as essentially an estimate of the total global willingness to pay for a 1 ton reduction in emissions of CH4 in a particular year. So these values, change over time. So they're sort of tagged with years as well. So we have a social cost of methane estimate for 2010, 2015, 2020, and so on. Those go up at some rate over time that depends on several things in those integrated assessment models. And so we have a schedule of all of those social cost estimates for each of these 3 gases over time and at 3 different discount rates, and an extra set of estimates that makes an additional assumption about something like tail risks. And these are intended to be used for the kind of use we're putting them to here. Policies or regulations that could reduce CH4 in this case, when a formal benefit cost analysis is done to estimate in sort of one fell swoop the climate benefits of making those reductions, we use these social cost numbers. So that's the purpose of these numbers. And yeah, that's the way we used them here. So let's go to the next slide. So yeah, this is sort of pretty much all the math in the paper in terms of calculating these total damages, is to take those the predicted changes in CH4 emissions that John talked about and the social cost of methane in this case to estimate total damages. This is a little oversimplified because, like I said, each year there's different numbers for both of these. And so there's total damages in each year. We discount those back to the present for some projection of changed flows of emissions to the atmosphere out to 2050 in our case. Okay, next slide, John. But we can spend a few more minutes talking about this when the next big question is, where does the social cost of methane come from and the other gases? And the answer to that is integrated assessment models produce these numbers. The 3 models that I'm still most familiar with from my time at EPA are the DICE, Fund, and Page models. Those were the 3 that were exercised in that interagency working group process. Gib Metcalf and Jim Stock have a paper out from a few years ago that gives a nice summary of that process and sort of where it stood then. Now the folks working on this still in the federal government agencies have been on something of a hiatus for the past few years, but now I understand or expect that process to sort of start back up again soon. This just kicks the question down one level. How does an integrated assessment model work? And so I have a few slides to give you a sense of that at a very high level, at least. So let's go to the next slide, John. So here's this says the simplest possible toy integrated assessment model. And this is just meant to give you a sense of the ingredients that are in most of these. The basic idea is to combine a model of the economy with a model of relevant parts of the Earth system, and then link those in some way. And that's what's described here. So a very simple version of this could have an economic growth function. This one just says we're going to grow at a certain aggregate income, is my capital Y here, is going to grow at a certain rate G over time. We'll be optimistic and say that's going to be constant You can pick the level that you think is realistic. We also have some projections of greenhouse gas emissions that could be linked to what we assume about economic growth. It's not in this case. This is just kind of an exogenous projection of GHG emissions. One reason this is a minimal model, but sufficient, is, we need projections of these variables over time to compute social costs of these greenhouse gases. Those projections want to be as accurate as possible. They don't have to be formally linked in the model for them to be accurate. We just need projections of them. So that's kind of the idea behind this simple version. So those are the two crucial parts for the economic model. The Earth system model has to have some biogeochemistry in it. The equation on the right-hand side here is just depicting a simple version of the carbon cycle, or at least carbon, the stock of carbon in the atmosphere. We've got emissions representing by that little x on the trailing end of that equation, emissions from all of the human sources. And there's some decay rate beta here, simple first order decay rate in this version. All of these are overly simplified, of course, but you can imagine as complicated a version of the carbon cycle as you want in these models. Certainly DICE, Fund, and Page have more sophisticated models than these, though some of them are not a whole lot more sophisticated, but they at least have 2 or 3 boxes in them, not just the single box version I'm showing you here. There's something like a global heat balance equation where the atmospheric temperature sort of increases with some kind of lag. And there's a radiative forcing equation. This is important because this is basically telling the model how sensitive the atmospheric temperature is to changes in GHG concentrations in the atmosphere. The lambda in that equation is written this way because that corresponds to the climate sensitivity parameter that that you might have heard of in this context. That estimates of that are around 3 degrees Celsius. And that just tells us that if carbon concentrations in the atmosphere double, we expect the equilibrium atmospheric temperature to go up by 3 degrees Celsius. So that's kind of a benchmark estimate for that parameter. And then there's got to be Earth economy feedbacks. And here that's represented by the simple damage function, where some fraction of our economic output is lost. The larger is the temperature and the atmospheric temperature anomaly. That's what the capital T is. So that this is just a simple nonlinear function to depict that idea. And like everything else, this rolls up a lot of, in this case, economic research that's trying to estimate how different sectors of the economy will suffer or otherwise from changes in temperatures. And that gets netted into these parameters of this damage function, the A and B in this case. And so whatever fraction of output is predicted to be lost at different temperature levels, sort of feeds back into that economic growth model. So I didn't show you the integrated version here, but I guess this is the equation that would replace this one to tie all of this together. So that's the simplest IAM that I can think of. Let's go to the next slide, John. And what you do with something like that is then once you have all these pieces in place, then you can compute the changes in projected economic damages if we change the emissions of 1 or more greenhouse gases into the atmosphere. That partial with respect to X is representing a 1 unit change in emissions of greenhouse gas X in this case. I keep thinking of CO2, but it's the same idea for all of the different gases. We reduce emissions of a gas in any particular year T in this case. That's going to have an effect on the climate and by extension the economy for many years in the future, because these gases stay in the atmosphere for some time. It takes them a while to decay. So we emit an additional ton this year. Some fraction of that stays in the atmosphere for some time. And so this is just accounting for the sum over time is accounting for the effect on the economy, ultimately, for all those future years, depending on how fast it decays. And so all those sort of increments of damage in each of those future years need to get discounted back to the present. And that's what that discount rate is doing in this equation. So each of these annual estimates of social costs are themselves discounted values. The way we put those to use then is multiply them by the predicted changes in emissions in future years, and then discount that stream back to the present to get a present value of those changed damages. That's what I guess the second bullet was trying to say, probably more cleanly. Yeah, of course, since these are discounted values, the discount rate R plays an important role here. There's a lot of discussion about what's the right discount rate to use. And in this, this kind of exercise, the interagency working group used 3 different fixed discount rates. A lot of economists will suggest you should use declining discount rates or treat discounting in a different fashion. But I at least am comfortable enough with the wide range of estimates that are in those official numbers. And that's what we've used in this paper. In an earlier version, we had used DICE, or at least the version of DICE that the interagency working group used. But in the end, we decided it made more sense just to use the quote unquote official numbers. Okay, let's go see what's on the next slide, John. Oh, yeah, you can actually exercise that little toy model is something you can put in Excel, and that's what I've done here. And it's easy enough to, set those parameters in what are reasonable enough ranges to match pretty closely the numbers that are published in the technical support documents. That's what's in that bottom graph there. The circles are the numbers we use in the paper. The dashed line is what that simple model predicts over that time span. And the graphs on the top are, in this case, what we're assuming about this is CO2. So this is social cost of CO2 I've run here. And so that top left graph is what we're predicting about CO2 emissions over time. We're going to peak in another 75 years, but then start to come down after that. And the red curve is what the model, that simple climate model, predicts about the temperature anomaly over time. Okay, next slide. Yeah, a little more about, that's still pretty rolled up. What's in the damage function is another important question. That's, like I said, that's trying to integrate a lot of research on the potentially detrimental effects of climate change on the ag sector, vulnerable markets, coastal sector. These sectors are, from Nordhaus and Boyer in 2000. One of Bill Nordhaus's books from 2000 gave the most expansive description of all of the different climate change damage studies that they use to calibrate their simple damage function. And so that's where these sector descriptions come from. More recent versions of DICE, as far as I know, at least up until a few years ago, made some changes to the damage function, but I don't think went back and revisited, the primary literature in all of these sectors to redo their estimates. A lot more work is going on now on climate change impacts to the economy, and so I hope and anticipate that more contemporary estimates of rolled up damages will make their way into newer versions of these IAMs, but that's still to come. All right, next slide. Oh, and this shows you, again, in that 2000 vintage of version of DICE, what the share of the total damages what share is attributed to each of those different sectors. Catastrophic impacts, even at that time, was a big share. Human health, agriculture, settlements. I can't remember exactly what settlements represents. I was going to say it has to do with sea level rise, but I see there's another sea level rise sector in there. So let's go to the next slide. I'm not prepared to tell you why the sizes of those pieces of pie are exactly as they are.
Yeah, that's a slide I made to show to my limnologist friends what the heck's
Sure.
bundled
Yeah.
in there. That's all. So here we
That's
go.
what's in, yeah.
Yeah.
Okay, so now we're sort of zooming back out to the methods and results from our paper. That, most of the slides I just went through was more background than we provide in that short Nature Communications paper, but that's what's behind the scenes for those social cost estimates. And maybe, well, there's at least a few economic assumptions on here that I can cover, but the assumptions about emissions over time, maybe at that point I'll hand it back to you, John, to pick up on those. But we've got discount rates. This is all borrowed, like I said, from the interagency working group results, and there's 3 different discount rates that were used there: a low 2.5% rate, a middle 3% rate, not much higher, but as you know, once the discount rate starts to get pretty low, it's the results are very sensitive to small changes there. And then a high, in this context, 5% rate. It is interesting to note, I guess, that most U.S. federal government official benefit cost analyses use 2 discount rates, a 3% and a 7% rate. That's sort of the standard rates to use in most cases. This the discount rates used in this interagency working group were a departure from that. The 7% rate was deemed too high for this very long run problem, and this 2.5% rate was added. So the 7% was replaced with a 5% as an upper bound, and this 2.5% rate was added to as sort of a compromise among all of the different ideas about how discounting should work and for such long time scales, put it that way. Emission growth rates, that's back to John.
Sure. Yeah, I can do that.
So yeah, I'll let you pick it up from here, and
and then
come back
I'll
when you
drop
need
it right back to you because you got I can do the next 2 bullets, but the emission growth rate of 0 is pretty unrealistic. That is, if we stay where we are totally, and that's nearly impossible in my view. So we took a kind of a low number there. 20% is absolutely minimal, and 100% is sort of a centrist center kind of number on summing the effects of the multipliers, like things like temperature increase and lake size times a lake increase, lake area increase, and the nutrient, sort of some conservative estimates of population growth and its effect on nutrients. So we didn't choose anything really extreme in order to, and clearly these estimates could be a lot higher. And then we did 2 different kinds of calculations of social cost, and one was directly from methane costs, and the other was by back converting methane to CO2 equivalents and calculating in that way, just because a lot of people are doing that sort of thing in literature, and in reality they weren't a whole lot different. But so those are those 2 bullets, and we can move on to the next one. And you want to do this one? I put Krona on here because I talked about some of this in Sweden, but and euros, because of course people in Europe might be interested too.
Sure, yeah, and I guess one thing to add about the emissions projections, those are, obviously projections of emissions from lakes,
Right.
Not sort of the background global
yeah.
emissions. So we're not making any different assumptions about that go into the calculation of the social cost numbers themselves. Maybe that didn't need to be clarified, but just in case.
No, that's good.
Yep. And so these are the numbers that come out when we do, we multiply those different versions of projections about lake emissions of just methane in this case, and discount at these different rates. So the rows, are different discount rate assumptions, and the columns are different emission assumptions. And these are, what are the units here, John? It says up there.
Well, I know it's
These are
87.
billions.
Yeah, these are billions of dollars. Yeah.
Billions, okay. Billions of US dollars, 2015. And so these are global estimates. And so the idea is, if we can change, tell us what the delta is here again, John. These are, one way to think about these is as the benefits of keeping projected emissions
Right.
flat, or go ahead.
Right. Yeah, it's just different rates of increased eutrophication-driven emissions, right? So a high rising would be 100% increase over the period of now to 2050. And present value low rising, I think we said would be 20% increase by 2050, which is also really, really low. I mean, it could happen if people get a whole lot more responsible on the planet with respect to nutrient losses, but I don't hold out a lot of hope.
So you can think of these as estimates either of damages, damages from the projected increases above today's
Correct.
levels, or the flip side of that coin is benefits if we're able to eliminate the rise at this point and just hold everything steady. Now, the difference between the top and bottom set of numbers is, like John said, the CH4 method is using those integrated assessment models with the numbers for methane in that biogeochemistry portion of the model. And so we're directly calculating in the IAM social costs of methane emissions. The traditional way to do this was to just use the social cost of CO2 estimates and then multiply that by CO2 equivalents that are calculated separately for each of the gases, which has its own set of sort of constraining assumptions that holds, at least has a very specific 100-year time frame that doesn't have to match what's going on in the integrated assessment model, and makes some other simplifying assumptions that make this just sort of an approximation of what we're really trying to calculate using the top method. So the top numbers are the ones that are calculated correctly, says us, and the bottom numbers are ones that are for comparison, because still, when a lot of people do this in the literature, they use this approach of just multiplying that social cost of CO2 times the CO2 equivalents for the different gases. So we at least wanted those numbers out there to make that comparison.
So it's 75 to 87 trillion, kind of with a high rising number and a low discount rate, right? So with a minimalist kind of approach of 31 to 35 at low discount and a very low increase in eutrophication-driven methane emissions. So even to a limnologist, that seems like a lot of money. So yeah. Should we move to the next one, Steve?
Yeah.
Okay. Well, I mean, part of the reason we wanted to do this is because our sense was that sometimes the assumption is made that the benefit of improving environmental quality is lower than the cost of improvement. And the costs of improvement are sometimes calculated piecewise. And you can clarify this into real economic terms, please, Steve. But we sort of do them one at a time: the tail of the elephant, the foot of the elephant, and you calculate what things like fishing and beach use and stuff are valued at. And then sometimes when we're doing cost or benefit cost analysis, the costs, the cost to society well, the benefit to society of preserving environmental quality is low compared to the cost. So we wanted to take these global estimates and compare them for at least one system, just to kind of do a case study of one system that's pretty well studied, to see how the global costs of methane emission compare to things like lost fishing, sport fishing, and lost beach use. Is that close to something that's understandable, Steve?
Yeah, I'm glad you said that, because it goes back to the motivation for the whole paper. We, like John said, we met at a conference that was all about applying integrated assessment models for valuing water quality improvements. And it came up at the workshop that, a lot of categories of water quality benefits, some categories can be and have been estimated kind of routinely by economists. Recreational fishing, benefits to recreational anglers is one example, big category. That's what we're going to compare to in a moment. Or beachgoers, how much enjoyment beachgoers get when the water quality is better versus worse, and those kind of categories. What had not been addressed before is the category we're looking at here, not local benefits, but that goes back to the title of the paper, but what are the climate change benefits of reducing eutrophication through these social cost numbers. So that's sort of what we're adding to the benefit cost literature now. The idea is that analysts have another category of benefits that can be included in those benefit cost analyses. And so what's on the remaining slides, I think, is a comparison we made for Lake Erie to the benefits we calculate for the emission reductions, to as apples to apples as we could get benefits for associated, I think, beach going and fishing in this case, like I said. So thank you for that reminder, Sean.
Yeah, no problem. It's what you guys have taught me. So, it's a great interaction. So, what you probably all know, Lake Erie's had major problems with nutrients and harmful algal blooms, and that seems to continue. And it's likely to be much more eutrophic by 2050 because laws aren't tightening very fast and so on. And there have been studies around that have estimated the cost of further eutrophication on recreational fisheries and beach use. And so we just wanted to make some comparisons to see if, what order of magnitude are we in with the global costs. I mean, that is to say, there's a local benefit to controlling eutrophication, but how big is the global benefit of controlling eutrophication in, let's say, one lake? And so we could do it for Lake Erie. So that's what we did. How much of this do you want to do? I mean, we didn't parse this out very well, but what you see on this graph, and we figured we needed a graph in the paper because everything was words and tables. And so we built a graph. And the graph basically shows the relative social cost of decreased fishing recreation in Lake Erie versus the increased social cost of methane emissions globally, of the same amount of increased eutrophication in Lake Erie. And then the bottom, and it's over an order of magnitude higher, the global effect of methane. So, I guess it's answering that question, is this important even on a local scale? And it's a bigger number now. And then there's beach closure, and the same kind of analysis that we made was, does the same amount of eutrophication change that would close beaches, does that cause methane emissions that would have a social cost larger, the same, or lower than the cost of beach closure? And this is closing all beaches on Lake Erie for the whole summer season, which is unlikely anyhow. But and I think you see there about an order of magnitude difference in social cost to 2050 between the global and the local. So I mean, my bottom line that I put over on the left is, when we control or reduce eutrophication, we win twice at least. We win at home by having better water and more local economic activity. We win globally by decreasing climate change costs. And do you want to add anything to that, Steve? I don't know if I did it right.
Yeah, I just emphasize this by thinking again, from the perspective of my former position, this would be a take-home message for me is, the big numbers that John showed on the previous slide do indeed look big, but I don't really, it's hard to know what to make of them for any particular case. This was our attempt to bring it down to something smaller that, we might deal with at EPA in terms of a benefit cost analysis of, some policies or regulations that would reduce eutrophication somehow in lakes, for example, Lake Erie, and the type of benefits that we're comparing to here, the fishing and beach closure benefits, are the ones that we're used to sort of pulling into those benefit cost studies. And so the question to my mind at that point is, well, those big global numbers, what do they translate into on a comparable scale for a real world benefit cost analysis? And this is our answer for this particular, sort of contrived case.
Yeah, it's also because referees kept asking and Sheila kept wanting to do this. So and this isn't in revision anymore. I didn't change that on the slide. It's published. It was published last spring or sometime in the COVID pandemic past. So we're doing something else. And we're just starting this. And so we'll just talk about it really quickly, I think. Oh, wait. Yeah, this I think is your slide because, yeah, you go ahead, Steve. You do this one and I'll do the next one with the license plates on it.
Okay, yeah, maybe this, maybe not the best order, but just as a preview to what John's going to talk about, we're trying to scale this down to the level of a US state in this case. And so John and another colleague have good estimates of emissions of all three gases from all of the lakes in one of these Great Lakes states, I believe.
One of those lakey states.
Yeah, it's a very lakey state. So there's tons of lakes. They all have their own sort of signature of methane, N2O, and CO2 emissions. And each of those gases has its own social cost schedule. So we can roll all of those up into social cost estimates, total social cost of greenhouse gas estimates for the lakes, and produce maps of those, which we hope will be useful for things like helping to design policies that would make actual reductions in, for example, runoff from farms that would have spatially differentiated impacts on lakes in the state. And so that's where we're driving at with the next few slides.
Right. And okay, so this came about because the governor of Minnesota was really, my state was really interested in the people in his office and Department of Natural Resources read this paper and they said, is there any way you could do this for Minnesota and let us know what it means for our state? Because we purportedly have 10,000 lakes and our license plate usually says land of 10,000 lakes, but it actually has 14,380 lakes if you consider anything over 10 acres. I've counted them recently. I have a paper on our website about it. Or it could have 117,000 lakes, depending on how big you're considering, or the total number is more like 4.6 million. But anyway, so I'm changing the license plate for the state of Minnesota. But and we got in touch with, here you see the three people who are working on this, arrayed on a scale from fun to formal, I know. So Leif Olmanson does the satellite work. So he's doing remote sensing of chlorophyll and actually over time and so on. So we wanted to know if we could monetize the benefits of eliminating eutrophication and methane across many individual lakes. And if so, where would we get the most benefit? And Olmanson measured chlorophyll in 1,000 lakes, about 10,000 lakes via remote sensing using Landsat 8 and Sentinel-2 imagery. And actually, as I said, he can hindcast these too, which is interesting. We haven't done this yet. And so then we wanted to calculate the see what this looks like spatially, as Steve mentioned, because it gives us a chance to look at the drivers, the local drivers of eutrophication and where we could have the biggest benefit. Anything more to say on that, Stephen? I'll go to the next. And now you're just going to see patterns. So this is a measles diagram of the state of Minnesota with Leafs Lakes on it. On the left, what you're seeing is milligrams of carbon of methane emission per square meter per day, calculated from the same models we used before. The cold ones are low, the hot ones are fast. And then the annual emission rates per lake, meaning considering area of the lakes, is shown on the right-hand graph, same kind of measles, but you'll notice some red dots that you didn't see before because these are big systems that have high methane emission rates. And then Steve took those emission rates and did the spatially explicit analysis of you do that part, Steve, and then we're basically done, you guys.
Yeah, that's just like I said, these are just methane emissions, but the lakes also have CO2 and N2O emissions. And so those the way they get weighted basically is by the social cost estimates for each of those gases that have their own time paths. And all of that gets discounted back to some number that turns into a color on these maps. So this is, if we had some policies that would reduce GHG emissions as a group or family, this is sort of the first order spatial targeting that you would want to do by lake if you could do such a thing. Of course, we could break those out into the different gases if we've got policies or regulations that affect the different gases emissions differently. So that's where we're headed with that.
Yeah, and we haven't done much of it. Leafs talked about it at one meeting, and this is the second time anyone in the world has seen this. So summary slide. Eutrophication is a powerful driver of greenhouse gas emissions from lakes, and there's big and significant. Methane emissions from lakes contributes 3/4 of the atmospheric climate impact of lakes. We're expecting eutrophication to increase a lot, like between 1.3 and 3-fold by 2050 and much more by 2100, unless we get smart. Polluted lakes will add to the atmospheric impacts of similar magnitude to burning fossil fuels and cutting and burning forests, which simply driven by eutrophication. And polluted lakes atmospheric impact will counterbalance nearly all oceanic and land-based carbon sequestration by 2050 if they grow at a moderate rate in eutrophication. We're looking at spatial explicit work. Lake methane emissions could have a social cost of somewhere between 6 and 90 trillion US in this present value estimations by 2050. And my bottom line always is, by sustaining and improving water quality, we win locally and globally. And I think Steve and I would love to answer any questions. We talked longer than we thought we would. Sorry, guys. I hope we kept you engaged.
Yes, I was very engaged. I think I could speak for everyone that in saying thank you. We could do applause, but I think it would just sound like noise probably over the Zoom chat. But I want to thank Steve and John and everybody for attending. So now I'll open the floor for questions. I have questions too, so I will jump in if there's a pause. But if anybody has any questions, please unmute, and then also unmute your video as well, and then we could see you can ask your question. So go ahead, and I'll jump in if there's not a question, because I have at least, I don't know, maybe 20 questions or something.
And I just jump in quickly. I noticed Sheila is here, or at least her name Tag is
Yeah.
here. And I
Hey,
hope she
Sheila.
doesn't mind
Hey,
being called
guys.
out, but I'm glad you were able to join. So you can take all the questions that the economists are directed to economists.
Yeah.
So maybe I'll open it with a question. First, I want to say, like, I'm just, seeing this. I was taking pictures of your slides just so that I could look at them again later. I don't know if you'd be comfortable in sharing them or if that's something you wouldn't like to do, but I feel like this was really, it illuminated a lot of things for me. And it was very cool to see that presented. But so you looked at local willingness to pay for in Lake Erie, and you showed that it was basically like relatively small compared to the social cost of methane or social cost of carbon equivalent emissions, right? Like it's orders of magnitude larger than methane, the cost of methane. So the question I had was in terms of so eutrophication is happening as a result of farming and nutrient management. So from either farming or from waste management. Do you have a sense for how much is coming from farming? Is it like the lion's share, or is it like, do you have any sense for that? Is it possible to remove, I guess this is directed to John, is it possible to remove the nutrients from through a waste management process? Is that happening in any place that you're aware of? And then, like, if you have give us a sense about how much farming contributes to this problem, that'd be really interesting to know.
Yeah, I think it depends a lot on where you are and what happens in terms of growth. Yes, nitrogen can be removed from wastewater pretty well. Phosphorus is the main driver, and it's really hard and expensive to take out of water. So once you put it in there, it's kind of in there unless you run it through sort of wetland systems and a bunch of other stuff that take up a lot of space. And so let me answer the farming versus everything else kind of question first. I don't know the answer. And then I do know that it depends a lot. I mean, if we were talking about the state of Iowa, where I used to work, it's the nutrient flux is basically predominantly agricultural nutrients, and it can be managed, and BMPs can be used to reduce it. But then, of course, it has some impact, although BMPs are supposed to be cost neutral, but it has some impact on profitability, or especially windfall profits in the case of really good production years, well, or maybe even bad production years. So in a place like that, then yes, I think you can assume that a lot of it is agricultural, but people excrete this stuff. Okay, well, and there are other sources too. And it's not just agricultural, like growing stuff. It's land-based application of manure from confined animal feeding operations. So I'm trying to remember all the population data, but population of, let's say, Iowa, which is highly agricultural, great state full of wonderful people. There are not a lot of people. And so let's say there are 1 million. I think it's about 1 million. And then we calculated based on body mass and excretion rates, all the pigs and cattle and chickens and how much phosphorus they release. And it's the equivalent of about 45 million people. That's just basically applied on land. So this is a lot of nutrient. But if you're talking about the city, New York City, similar, really big city, it depends on where that nutrient goes, whether you can sequester the phosphorus in some way. So there are a lot of good technologies for it. And the other part that's really important is from the standpoint of economics, we need phosphorus fertilizer to grow good crops, right? And there's a strategic world shortage of phosphorus fertilizer. And it is a dangerous one politically, in that it's the big guano mines and stuff are almost all in very unstable, difficult places. So reclamation of phosphorus is something that's happening really a lot. And I could see a really positive benefit to taking all that sewage and pulling phosphorus out of it and reusing it. And about 50%, this may be more clinical detail than you want, but 50% of the phosphorus you excrete comes out simply as urine. So it's really easy to chemically to do something with. So there are good possibilities there, but I can't tell you worldwide how it all shakes out. But the problem is every human that comes onto the planet is going to need another kilo of phosphorus annually that they're going to excrete. And it has to come from some production system that also loses nutrients. And I'm sorry, David, I can't give you the clean answer. I'd love to.
No, I think that was a really illuminating answer. Knowing that it's phosphorus, that's one of these major contributors, because we actually had some projects here that were looking at N balance, but like looking at nitrogen balance on in fertilizer, and looking at nitrous oxide emissions from directly from field applications, from over application. And so that's within our climate smart ag program here at EDF. So thinking about phosphorus and thinking about the water pollution effects having significant climate impacts, that's actually kind of new thinking to us, or at least to me. I'm not sure, I can't speak for the scientists here, but for me, I saw it and I'm just like, wow, that's a big number for coming from phosphorus. So just, I think putting this on the radar is really important. Maybe even having a continued conversation with you all about how, what levers could be pulled to improve this in the places in the world where this is a problem. Because I think there's probably some low-hanging fruit. There might be some money that is already in some of these federal programs, like clean water, state revolving funds, that sort of thing, innovative approaches that could be taken to address this problem. But just knowing that we have a problem, here it is, and this is what it is really helpful. So yeah, no, all your detail is really appreciated. There's two things in the chat. So I can ask Mark Kitson to speak up if you'd like, or I can ask the question for you. Happy to do so. I can ask the question. So it says, which GHG emission was not affected? Oh, I'm sorry, go ahead, please.
I was just a little slow to the unmute.
That's okay.
John, when you were giving your slides in the very beginning about greenhouse gas emission as it relates to lake size and trophic status, which greenhouse gas emission was not as affected?
Marty, everything was affected both. Well, just a second. I'm going to the slide so I can remember it, because I get mixed up in the multivariate things. But so CO2 is decreases with lake size. So bigger lakes, less CO2. And the effect of trophic status differs between large and small lakes. So large lakes, as you increase nutrients, they emit more CO2. Okay, but small lakes, not as much. And then methane emissions were unaffected by lake size, and it was all driven by eutrophication. Now, that's not to say it has no effect. It's just we couldn't detect it with 8,000 lakes or so worth of data. So there probably is. I would suggest that there is some lake size effect, but we didn't detect it. And nitrous oxide emissions increase with lake size and trophic status. So big green lakes kick out a lot of N2O, which makes a ton of sense when you consider that everything that's denitrified, meaning going from nitrate to nitrite to nitrous oxide, and then on the way to nitrogen gas in the atmosphere, about 20% of that never makes it to nitrogen gas, but goes off as nitrous oxide. And then, once it hits the atmosphere, any atmospheric moisture comes down as nitric acid. So it has an acid rain component too. So they were each a little bit different. I'd love to have more data, and a lot of data are coming out. It'd be really fun to be able to, make those models. These are just big global empirical models. It'd be nice to make them more exacting. Thanks.
Thank you.
So I have another question, unless there's any more questions. So I will jump in. So the 6 to 90 trillion, I just want clarification just to make sure I understand the paper. So you're saying that you have a predicted increase in eutrophication that's going to occur to 2050, and the value, present value of that increase in methane is 6 to 90 trillion, right? That's what you're saying. Is that correct?
Yes, that's the present value of the damages that come from that increase above the current level, not of the total emissions, but the increased emissions over today's levels. Or conversely, I like to think of it as if we had a policy that would hold the line where we are now with emissions, then the benefits of that change, and again, present value terms, would be those numbers.
Mm-hmm. And you used DICE originally, or did you? Because I remember you mentioned that you said that you used DICE and then you reverted to another model. Which model did you actually use for this?
We just use those numbers that you can find in the tables and the technical support documents. So that that's the outputs from using DICE fund and page in the particular ways that are described in those technical support documents. What we had a version of DICE that would mimic what the interagency working group did with DICE, but also you had the specific gas components in it as well. But those most recent numbers from the technical support documents are gas specific, and so we could do the same thing and not have to use the CO2 equivalent conversions.
Yeah, I thought your description of the IAM was really good. I had not seen such a condensed, like a toy model that could be described in a presentation setting. Oftentimes those who operate those things, like they talk about maybe one portion or something, but you're able to kind of summarize it in a way that I thought was really coherent, and I really appreciate that. It improved my understanding of IAMs.
Okay,
considerably.
I'm glad that was useful.
Yeah.
That was the purpose of, I have for my own purposes, I have to, before I feel like I have any understanding of what the models are doing, make a very simple version, and that's what that was for.
Yeah, I wanted to add just another piece to the answer, and that is, well, I also appreciated that explanation, the toy model. That was really helpful for me. Thank you, Steve. But the other part is, if you decrease eutrophication, then there's another benefit. And we were asked at one point to do those calculations, but it seemed so outrageous to think that with increasing population and increased temperature and everything else that we could decrease eutrophication. That I don't think we refused. I think we did some calculations, but I mean, that's another way to look at it, that you could benefit. There could be a benefit, a global benefit, to decrease baseline methane emission.
Yeah. I think it's, if there's a policy or like some technology like you were talking about before that is relatively inexpensive to employ, or even if it is expensive, it seems like it could be justified with these costs. I think that what I'm like, I was very surprised by these costs. I mean, I was surprised by how large these numbers are, and I was puzzled a little bit, because I'm like, because I didn't know much about lake systems. I was trying to think about, could lake systems be a carbon sink? Because we're talking about nature-based climate solutions often here. Like, this is actually kind of the current conversation at EDF. We're thinking about using natural systems as ways of storing carbon, and lakes may. So there's a question, and it's wrapped up in this. Can lakes be? Or can you think? Should I be thinking about lakes as being like avoided emissions, like a potential source of avoided emissions? And would they ever be a carbon sink? I mean, because that seems like you'd have to completely reverse eutrophication, but then at some point there's going to be some equilibrium between lakes and the environment. So just to get a sense for that, like, how should I be thinking about lakes in terms of a nature-based solution?
They're both. I mean, they're emission sources. They can be emission sinks too. Some of the lakes that are highly productive are sucking in CO2 from the atmosphere, but only for short periods of time. But the carbon that goes into a lake is so huge compared to the emission numbers that they actually are very, very good carbon sequestration sites. And there, I got a fair number of papers on that, but lakes hang on to carbon incredibly well once it gets into the sedimentary environment. Some portion of that then is turned into methane and CO2 and sent off to the atmosphere, but there's so much carbon that moves through them that it also can be a sequestration site as well as a source of emission. I mean, I have a Halloween story on International Public Radio that I did some years ago, talking about the amazing ability of lakes to sequester carbon, including bodies and dead stuff. And it's quite amazing how they, I know, Steve, it's disgusting. This is where anyway, but the dean of New Jersey College for Women was preserved for 60 years in the bottom of Saranac Lake and looked like she just drowned. I mean, they're really good at holding on to carbon. So yes, yeah.
That's a remarkable story. It sounds like a perfect Halloween story too. That frightens me. But at the same time, so then would you say on net, like lakes actually do sequester, so they sequester more carbon than they emit, or carbon equivalent than they emit. So when you reduce their emissions, you're just improving it as a sink. Would that be safe to say, or is that?
I think that's a good generalization. If you can keep them from, if you make them less eutrophic, I mean, there are other things involved, right? Because you're also passing carbon downstream. It flows out. So more flows out than flows in. But when we figured out how much carbon dioxide was going off to the atmosphere, we had to revise the terrestrial export numbers because they were based on river export to the oceans. And then there was another chunk of this that was gas loss to the atmosphere that no one had paid any attention to. So yes, I think generally that's something you could say.
Okay, I have just been pinged by Hillary. So Hillary, I want to thank you for putting this on. Hillary Collins was the one who organized this whole meeting and got Steve and John set up. So Hillary, thank you. And then I want to thank Steve and John for coming. So Steve Newbold and John Downing, please, a round of applause from everyone. Thank you so much for being here. I would love to introduce, we recorded this. I'll ask you later, if you're comfortable with me sharing this with some of OCS, but I think that this is really valuable work, and I'm excited to learn more about your future work, but then also to connect you to EDF to see if there's some opportunities here to use some of your work in policymaking. So thank you again. And Sheila, thank you for being here as well.
That's great.
Okay.
Thanks. It was fun to see somebody else present. Always good to just relax.
No.
Yeah, it's great to see you, Sheila.
Good to see
This
you
was
today.
really fun. I really appreciate it. It's really fun for me to have been with you today. It's really great fun.
Thanks for
Thank
having
you.
us, David. It's great.
Yeah. So
Take
long.
care.
Have a good
Thanks,
one.
John and Steve.
Bye, Sheila. Bye, everyone.
Bye.